Yes, I already, talked about that, expanding it into 3 dimensions. And the last thing that I want to talk about with this particle in the box problem, which is really, really cool, a cool application, is the particle on a sphere model. So as we established, right, we can easily convert this into 3 dimensions, psi x, y, z. Okay. What will become more practical will be to expand this into psi r, theta, and phi. All right. And when you do that, so this del squared right here, that's what this thing is. That's showing me the 3-dimensional second derivative operator. Okay. If I expand this into r, theta, and phi, then instead of doing a particle in a box, I can describe a particle in a sphere, which is a lot more physically practical. So for example, suppose now I'm just drawing you my XYZ coordinate system, okay? And so let's establish the boundary conditions. So maybe instead of, putting my particle in a box or in a 2-dimensional plane, or even forcing my particle to be, in a cube, particle in a cube, what if I said the particle has to exist somewhere in this sphere? Well, we can do that problem. It's really nasty because you have to make this coordinate transformation. However, the solution is nearly identical to our particle in a box solution, which is really cool. So again, our particle in the box solution, let's find one written simply here. Where did it go? Yes, n squared h squared over 8ml squared. Particle in a box. Well, you can do this substitution of variables for the 3 dimensions. You can transfer it to an r theta phi coordinate system, which is going to be challenging, and that's where we're going to start working towards next. But you still get a solution that's practically identical to our particle in a box solution, which is really cool. So, and this also establishes the same situation with n. N equals 1, 2, 3, 4, etc. Okay. Me, that's the mass of an electron. Okay. Mass of electron. And now this r is the radius of the sphere. Okay? And so we established the same thing here. All right? As, what I want you to call, what we established, as the box gets bigger, right? And now it doesn't matter at this point if it's a box or a sphere or a plane. It's the same physical implication. Okay? So as our sphere gets bigger, the energy has to get smaller, right? So if the energy is getting smaller, that means the wave that fits in this box or sphere or whatever, right? I'll go back to just the very simple 1D result here, right? Our simple 1D result shows you, right, as I make this box bigger, look, the wavelength is getting bigger. As I make the box smaller, the wavelength is getting smaller. So what does that mean for physical reality? Well, look, here are some quantum dots that somebody synthesized. So quantum dots are, it's a fancy word for a nanoparticle. And these are nanoparticles made up of cadmium and selenium, okay? And here are the, I believe these are the diameters of the particles, okay? And you notice there's a really cool trend. The very small particles appear blue to our eyes. The bigger particles appear red to our eyes. And as the particles get bigger, they push more into the red end of the spectrum. Or in other words, as the particles get smaller, they push more into the blue end of the spectrum. This is a direct result of the particle in a box or particle in a sphere phenomenon. So in other words, in these nanoparticles, right, these nanoparticles are these little spheres. And they have electrons. They have a lot of electrons in them, but all the same, they have an electron or a mole of electrons in them. Okay, those electrons have energy level n squared h squared over 8 me r squared. And so as these nanoparticles, as they actually get bigger, they become more red. As they actually get smaller, they become more blue, which is really, really cool. And this is a really cool phenomenon that you all can do in the lab on free rotation experiment, those of you that are lab students. There's an experiment that we can do synthesizing gold nanoparticles. And we can synthesize different sizes of them and establish through their spectrum, we can figure out what size they are just based on where they absorb, right? As they absorb out to the more red end of the spectrum, we know they're bigger. As they absorb down to the blue end of the spectrum, they're more blue, okay? So this particle in a sphere, particle in a box problem, it has real physical observables, right? I'm always saying that word, physical observables. This is a physical observable of the particle in a box problem. The observation that color of an object changes with its size, okay, which is very cool. Okay, so really